Welcome back, everybody. Today we're going to discuss hypothesis test for proportions. All right, just a reminder, you can pause the video and take a picture of the steps I'll be utilizing in the hypothesis test and the assumptions for the hypothesis test. We're going to be looking at a single sample for proportion. So I want to make sure I have a random representative sample, a binomial setting, and I want to make sure I have normal via the CLT, central limit theorem. So let's get right into the questions. We have a TV company that wants to know if their customers would upgrade to a new package with new channels if the price was lowered. We surveyed 400 customers and found that 125 would upgrade based on the new deal. The boss is willing to use the new promotion if we have over 25% of the customers willing to upgrade. Is there evidence at a 5% level of significance that we have more than 25% of the true proportion of the population? Very good question. And so what we're going to do here is we're clearly going to run a proportional test. Look at the question. Is there evidence? That's a hypothesis test question. We have more than the true proportion. This is truly a proportional test. And that means we're going to utilize the steps in a proportional test. They're the same steps in a hypothesis test. We just got to be careful in how we write things. So first of all, we got to be careful in the hypothesis. We're talking about proportion, so we need a proportional symbol. And again, the alternative is usually in the question. And here it is. We want more than 25% of the true proportional population. So that's what we're looking for, is we're assuming the proportion of the population is 25%. I want to show that it is more than 25%. All right? That's what we're trying to show, that we have more than 25%. And that equal to is actually less than or equal to, if you want to be very clear. The alternative is we want greater than 0.25%. And so the no would be, yeah, we believe it's less than 25% currently. The boss will not take an initiative, will not enact any program unless we get over 25%. So we're testing that theory. All right, once we have H0 and H1, now we collect the relevant data. We collect the relevant data. In a proportional test, really it's very easy. N, P, and alpha. Those are the relevant values that we need in our data set. So let's go back to the question. So the alternative, and let me give me a little bit more space here. The alternative would be a greater than test. It's a one-sided greater than test. It's good to know that. My sample size, we'll read it. We had 400 customers we surveyed. Our P is sample percentage that said yes. Sample percentage that said yes. How would you build a sample percent here? Well, the number that said yes would be 125, and that's based on the 400. So my sample percent that said yes is 31%. The question is that far enough over, all right, is that far enough over the threshold of 25% for the boss to enact, to go forward with the new proportion? Good question. Well, before I move on, I'm going to add actually a couple things into here. I do want the standard error, and we'll talk about what that is. It'll make my calculation easier. And then we'll want the alpha value, and then we'll get our test statistic. So I'm upgrading the steps to show some more information that's helpful. The standard error, the alpha, and the test statistic. All right, so first I'm going to run the checks. I like to make sure I'm going to use the Z distribution, the normal distribution. I need to have the right to use the normal distribution. To have the right, in this case, to use the normal distribution, in our survey, we needed enough yeses and nos in our survey. Well, we had 125 that said yes, they would upgrade. That would mean 400 minus this number would say no. Both of these are at least 5, and because they're both at least 5, we get the central limit theorem that says we have normal. That's important to me. We have normal because of at least 5 people say yes and no to my questionnaire. If that was not true, we'd have to do some binomial correction to do this hypothesis test. The good news is we have at least 5 yes and no's to this question, so I can utilize the normal. And that's awesome to do. So there's my quick check. Please be careful that this had nothing to do with n being over 30. The n over 30 is only something we look at when we're doing an average hypothesis test. We're looking at a proportional hypothesis test, and we need to understand in a proportional hypothesis test, we're looking at least 5 yes and 5 no. That's the criteria to run the test statistic, the z-statistic. All right, so how does one build the z-statistic? Well, to build the z-statistic, you need the correct formula. Let me go to the formula sheet. That would be the correct formula for the z-statistic. How do I know? Well, in my formula sheet, under hypothesis test for proportion, I have this formula. This would be the z-statistic. So I'm pausing to give you a chance to either pause the video or take a picture of it. That is my z-statistic. The denominator is called the standard error. All right. The denominator in your statistic is usually your standard error. So that is my standard error. My standard error will equal the square root of pi. Now, pi is the national percent we're trying to compare to, which was 0.25 in this case. So it's pi times 1 minus pi. In this case, 1 minus pi is 0.75, right? Divided by n, which is 400. And so that's our standard error. I realize now I should have left room for the variable pi because that's going to be helpful to have when we do the values too. So I can insert it right here with no harm, no foul. So we'll insert pi here. Pi is 0.25. How do I know? Because we are testing against this value of 25%. This is the cutoff, the threshold that I'm worried about. And so that's why that's my pi. So there's my standard error, 0.021 or 2.1% or 2.2% if you're rounding. All right. So the standard error is we're typically off by 2.165%. Alpha, that's in the question. The alpha is 0.05. That's in the question. The level of significance is your alpha. All right, your test statistic. Your test statistic will be your sample, the 31%, minus what you're trying to look at, the threshold, 25%, divided by the ratio factor, the standard error, as I call it. And that's usually how you build a test statistic no matter what test you're running. It's usually your test versus the national statistic divided by the standard error. And that's what I have here. And so that's my test statistic, 2.88. And that would be your z-test statistic. All right, let's bring this back over here. Because what happens in a hypothesis test setting is you give your no, you give your alternative, you collect your data like we did. And so we collected the data and we found our z-statistic to be 2.89. And yes, you should write down the formula you're utilizing for the z-statistic. That's p minus pi divided by the standard error when it deals with the proportion, which is on my formula sheet, the square root of pi times 1 minus pi divided by n. So the z-statistic's 289. Awesome. Now, there are approaches. We're going to use the critical value approach first. No problem. To build the critical value approach, recall from previous videos, you need those two pieces. Greater than means we're going to have a bar on my z curve that's on the right-hand side, and all of alpha goes to the outside of that bar. Alpha in this case was 5%, so this area over here is 5%. And this is the rejection region, the critical region. This is where we reject H naught. If we fall over here, we do not reject H naught. So this all comes down to what Z value bounds this top 5%. So to find it, if you've been playing at home with my other videos, we're going to use norm S inverse. I'm abbreviating that as NSI. Norm S inverse of the area below, which is 95%. Think about it, people. If 5% is the area above, then 95% is the areas below. And that's it. NSI of 0.95. Let's go check that out. I'll put that in my critical value. This will be the norm S dot inverse probability, and probability is always probability below, and that would be 0.95 in this case because it's a one-tailed test. And my critical value is 1.645. Please note, you could pause the video at any time and check the code. I try to leave it there for a few seconds so you can check the code I have written. And I guess I should have done that up here. And I should have done that for the standard error. So I apologize. Standard error is my denominator. Test statistic is my p minus pi divided by the standard error. My critical value is based on the picture, and that's 1.645. And there it is. 1.645 is my critical value. I just got to put my test statistic in this picture. Is it in the blue region or the red region? Well, if the barrier is 1.645, 2.89 exceeds the barrier, and that means, conclusion, I reject H0. Because my statistic is in the rejection region, the critical region. Done. But of course, as I've mentioned in previous videos, sometimes we look at the p-value approach. So the p-value approach, and the reason we look at the p-value approach is because the p-value is based on your data, not some arbitrary alpha somebody gives you. The p-value is based on your number, 289. So your number is 2.89. The p-value is the probability you can run the study again and get a more extreme value. So it would be aligned to this area. That would be the p-value, is to find that area. Okay. So to find the p-value here, I'm going to, please understand, you're using the z-distribution. So everything should be norm here, all right? This is the z-distribution, so you should be accessing the Excel file norms. So what I'm going to use here is norm S dist, but I got to be careful. Think about it. I can't just use norm S dist. Norm S dist, comma 1, because it's always cumulative, but you can't just use norm S dist here. You have to adjust it to get that red region. I'm giving you a moment to think about it. You see, norm S dist gives you the area below. 1 minus will give you the red region. And that's how I would adjust the formula to get the p-value. Norm S dist says, hey, you give me your bar, your z bar, I'll tell you the area, which is the probability below. Norm S dist gives you the probability below. If I want the probability above, which is the p-value in this case, you have to do 1 minus. And so here we go. The p-value will equal 1 minus norm S dot dist of the z value, well, your test statistics right there, comma, yes, it's always cumulative in a basic level statistics class. And so there's my answer. There's my p-value. As a percent, that's 0.19%. So I know my p-value is 0.19%. Well, my friends, that's less than alpha, which, once again, what was our alpha level here? Alpha level was 5%. Our p-value is less than alpha. All right, our p-value is less than alpha. If your p-value is less than alpha, you do reject H0. If your p-value was greater than alpha, you do not reject. So once again, our p-value is less than alpha, so we reject. Some people prefer the p-value because now you can say, well, wait a minute. If I even make alpha a little bit more stringent, alpha is 1%, I still reject. It kind of gives you the ability to look to see if your p-value is sensitive, if your data is sensitive to alpha. Remember, recall, alpha is your type 1 area probability, the type 1 error probability. So Alpha, we typically set at 1, 5, or 10%. Notice this p-value beats all of them. This p-value is not super insensitive, it's super special. It's triple star significant is what I want to say. This p-value in reports would be triple star significant because it's under 1%. All right? You can see that in some reports. The stars represent how significant. 1 star is 10%, 2 stars 5%, triple star is 1% significant. What it means is under 1%. This is a very significant example we have here. Sweet. So once again, we reject. And we could cleanly see that in Excel. This p-value is under alpha, so we reject. My test statistic is over the critical value, so I reject. Both of these reject. What does that mean? Well, it means we don't believe in the 25% anymore. We believe that it's clearly over 25%. The boss could say, well, how much over? Well, that's when you build a confidence interval. All right. When you reject and you don't believe in that statistic anymore, the 25%, and you believe it's over then because you've tested the more than, the greater than, the question could be how much over? Well, that means we got to build a confidence interval. So how does one build a confidence interval? That's a good question. And why am I building a 95% confidence interval? Because I feel like it. You build whatever you feel like, 90, 95, 99. Heck, you could build all three if you just follow my steps. So what's the 95% confidence interval for proportion? Well, it captures the true proportion pi. And I guess I should pause here. Yes, I'm using pi as the true population proportion. It is not 3.14. I do apologize. I am using pi as the population proportion. How can I capture it? Well, you would capture it using p, your sample percent, plus or minus z times the square root of p times 1 minus p over n. This back number is known as the margin of error in a confidence interval. Please see my video on confidence intervals for proportions to find more details and more examples on this. I'm just utilizing the fact that to come to hypothesis test, you've probably learned how to build confidence intervals. If you're weak on building confidence intervals, I do ask you to go back and look at that video. Look at the letters you need, P, Z, and N. You already have N and P. You need to have Z. To build Z, you need to understand the picture. It is a confidence interval, which means you have two sides. 95% is in the middle because that was the confidence interval I wanted. So it all comes down to what Z bounds this picture. Well, to find the Z, I once again am going to use norm S inverse. Norm S inverse only works on the area below the bar. So take a moment. How much area is below that bar there? If you said 975, you're rolling with me, and that's awesome. Again, why 975? Well, think about this area. This is 2.5%. And so that means the total area below is 975. So I got to go to Excel now and find that bar. And so that bar would be equal norm, not nom, norm.s.inverse of 0.975. And we get 196. And once we have 196, then we can build the confidence interval to create the upper bound and the lower bound. So let's do that. So we need the margin of error. Well, the margin of error is equal to Z times the square root of P times, parentheses, 1 minus P divided by N. And I'm going to pause to make sure I've written this correctly. So again, it's Z times the square root of P times 1 minus P divided by N. Excellent. So my margin of error is 4.5%. To find my lower and upper bound, the confidence interval is always built the same way. Your sample, P, your sample center, minus the area you've built, and the upper bound is always built the same way. Your sample center plus the margin of error. And there is my confidence interval. 26.7% on the low end And on the high end, 35.8%. And as a triple check, when I build my confidence intervals, I notice the population proportion I was studying, which was 25%, is not between those two numbers. 25% is lower than the lowest bound. That's why I know I definitely have more than the 25% in the customers. Not low, I should be careful. I am 95% confident that I have enough people that will buy the product at a significantly lower discount. All right, we've definitely hit the 25% threshold the boss wants. I've rejected twice, and I've built a confidence interval that does not contain 25%. They're actually both, the lower bound is higher than 25%, and that's what I wanted. So I have 3 checks to say I'm heading in the right direction. Awesome. So we've done all the math. The only thing left now is to summarize it all, just like you would see in a journal or in a quick report. If you're writing a report for the boss probably won't care about all the work we just did, all this beautiful analysis we just did. They want a summary. So here we go. We give them a summary. I reject H naught. That is pi is equal to 25 or less than or equal to 25%. How do I know that? I know that because my test stat. What was your test stat again? What did you get when you did your study? You got 2.89. That's in the critical region. That's one thing if you love the critical region test. If you're not a critical region test, you state my p-value. What was our p-value? Our p-value was roughly 0.2%, 0.19, round up 0.2%. And that's clearly less than any alpha you give me. Even the alpha you gave me, boss, which was 5%. You gave me 5%, but guess what? Mine is insensitive. That means it's lower than 1%. It's very significant. That's why I reject. What does that mean? Well, that means I don't believe mu is less than or equal to 0.5. I actually have evidence. I have evidence that the true proportion of blah people that would upgrade to the new product given a substantially lower discounted price, and that's what I have. I have evidence that the true proportion is blah, 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 blah. The true proportion is greater than 0.25. The true proportion is above this 0.25 cutoff. I believe you'd want to roll out the promotion. Of course, the boss could come back and say, do you have a confidence interval on that? Well, yeah, I am 95% confident that, and we're going to use the symbol pi. Pi represents the question, which would be the true percentage of people that would buy the product. I am 95% confident that the true percentage pi, the true percentage of people that would buy my product at a substantially lower discounted price, is between, on the low end, 26.7%. And notice that's above the threshold you want. And on the high end, up to 35.8%. And that would be my summary I'd give to the boss. I'd say I did a hypothesis test. I ran it with the fact that I would reject the null if this is my null. And of course I rejected because my test statistic fell in the critical region. My p-value is super special, super significant. You gave me 5% alpha. I was even able to conquer 1% alpha. Which means I do have evidence, boss. We do have evidence in a survey I created that the true proportion of people that would buy the product is over the 25% threshold. So, and in fact, I am 95% confident that the true percentage that would buy this product at the substantially lower discount is somewhere between those two markers. And that's my conclusion. Again, the boss only cares about the conclusion, right? When you read the journal article, you read the summary quickly. But then you go into the methodology. You go into all the work, and that's what all this is. The methodology and the research needed to get you to this quick little summary you can read about how effective this new promotion will be given a substantially lower discounted price. Awesome. And that takes care of example 1. All right, guys, why don't you pause the video? Why don't you try your hand at example 2, and then I'm going to fire off on it. All right, we're back. So, now that we did one in detail, nice and slowly, now I want to speed it up and just kind of go through this one quickly. So what do we have here? In 2010, the state of Massachusetts enacted a law that forbids cell phone use by drivers under the age of 18. Prior to this law, an insurance company found that 80% of teenagers did use their cell phone. So that's kind of like our pie. And of course, like before, I'd like to have kind of the same things going on here. So I'll just copy that down and paste it. I'm going to have to tweak these numbers to make it reliable again. So we found 80%. That was the pie, 0.8. Notice certain things adjust, and that would make sense. I have formulas written based off of things. So pi is 0.8. The analyst sampled 200 drivers. So that's my sample size, 200 drivers. Okay? And we found that 158 still did use their cell phone while driving. So equals 158 divided by our 200. So it was 80% did it. The Massachusetts enacted a new law. Did the number of people using cell phones come down considerably? And that's what we want to know. Did this law have any effect? Is 79%, is a 1% drop that much of a difference? Well, we need to talk about this. First, before I can use the z-distribution, I must check to make sure I can use it. You should always run your assumptions. How do you know your assumptions? Remember the steps. Single sample for proportion. Do you have a random sample? I'm going to assume whoever collected the data collected this data randomly and representatively from all drivers in Massachusetts. Is it a binomial setting? Of course it is. 400 trials, either they did or did not use a cell phone. And we had a pass percent. So we have all the key ingredients to a binomial settings. And can I use normality via the central limit theorem? This is part of your research. You check off each and every one of these assumptions. Random representative. You're collecting the data. Make sure the data is collected randomly and representatively from all the Massachusetts drivers. Binomial. Make sure it's a question that's binomial. Yes or no, they use the cell phone. It's a binomial setting with a pass percentage of 80%. Pi. Got it. Normal. Well, can we utilize normal here? The answer is yes, because the number of people we found still using the cell phone was 158. So the number not using it, well, we got to adjust it. It's not 400. Be careful. It's 200 minus. So the number of people no is 42, and both of them are at least 5, and that's to check for normality. We need at least 5 people that say yes and no to your question, your binomial type of question, to pass the central limit theorem to give us normality. If it's under 5, you have to go back and look at binomial corrections and using the binomial distribution. More of an advanced stats type of question. In this case, we both got 5. Awesome. Over 5. Nice. That means I can move on in the process. Now, what's my alternative here? What's my test? Is there evidence the law had any effect? Any effect is not a greater than, and any effect is a not equal to test. That's really what this is a not equal to test. So if I want to set this up quickly for this example, my null is, I believe it's at 80%. I want to show the law had some type of effect on people using cell phones in that age range. That's what I want. I want to show you that there was some change based on this new law affected. Or I want to show you that there's no difference in some respects. We'll see what happens. But I want to show if there's evidence the law had any effect. Now we collect our data. Our data, of course, will be alpha, N, P. And that'll lead me to build my Z statistic. And that's what I'm going to do now. I'm going to build my Z statistic. The great news, the standard error remains the same. Actually, I lied. I didn't make this formula correct, did I? The standard error is based on pi, and I didn't write it in terms of that. Now I'm going to do that. Square root of pi times parentheses 1 minus pi divided by n. That's the formula for the standard error. Another parentheses I need. It would be, again, pi times 1 minus pi divided by n. So I'm automating it in this example. In the first example, I did not automate it, so I'm doing it now. And so there's my new standard error. Alpha, got to change my alpha, right? Alpha here was 10%, so let's put that in there. My test statistic, that shouldn't change. My test statistic is p minus pi divided by the standard error. So there's my test statistic. And so that's the first thing I wanted to find, my test statistic, negative 0.35. So my test statistic, my Z-stat, as we like to call it, is negative 0.35. All right, time to build the critical region. Well, this is a two-tailed test, got 2 bars. I need to find the Z so that my alpha, what was my alpha here? Let's check. My alpha was 10%. So that the area outside of both bars is 10%, which means both bars capture an area of 5% on the tails for total area 10%, which is alpha. Alpha is always the area outside the bars in the critical region. So to find that Z value, I'm going to use norm S inverse of 0.95. I'll let you think about why I did that. So my critical value, it's the same number, 0.95, which is 1645. Cool, I got lucky. 1.645. That's not automated. I just got lucky. It's the same as example 1. Notice it's 0.95 as per the previous question. Just got lucky. 1645. Nice. So my Z statistic, where does it fall? Here is the threshold, 1645 and negative 1645. My number falls here, well within the do not reject region, well within the DNR, the do not reject H naught region. Clearly, my sample is not special. Clearly, when I did this study, I'm finding evidence of do not reject. That's what I'm going to have here, is a DNR H naught. Because my test statistic is not over the critical value to get in the critical region. So I would not reject H naught. Okay, it happens. The sample I collected was not significant enough. The law may have had some effect, but according to my data, I don't have evidence to support that at a 10% level. All right, we can check the p-value. Let's make sure the p-value is written correctly. It is not. All right, we must adjust the p-value. So let's do the p-value approach, because some people really love the p-value approach. I love doing both. They're kind of checks to me. They should do the same answer. This one did not reject. I better get the same answer down here. So the p-value, how do you build the p-value? Well, again, remember, this is a two-sided test, and you utilize your statistic, negative 0.35, and symmetry-wise, that would be 0.35. And so the p-value is the area or the probability you're more extreme than your test statistic, which would be this red region. That would be the p-value. When you're going step by step, you should really draw these pictures and show that work. When you're in my class, I want these in those steps. If I want the p-value, I expect a picture, and then I expect the code underneath it. In this case, it's a Z. It always is a Z when you're doing proportion. But got to be careful. There's 2 regions, so I'm going to multiply by 2. And I got the negative Z value, so I'm just going to do norm S dist of the negative Z value, comma 1, because it's always cumulative, and multiplied by 2. Why multiplied by 2? Well, the norm S dist gives me the area below the bar. So the norm S dist will give me this area. These areas are symmetry equal. So if I multiply by 2, I get the total area, which is the p-value I wanted, which is, that's not Z. That would be the p-value. So let's write that in there. it would be equal to 2 times the norm S dist of your test statistic, comma, 1. And I get 0.724 or 0.7237. All depends on how much accuracy you need. 0.7237, which as a percent is 72.37%. Well, that's well over any alpha. That number is greater than any alpha. And if your p-value is greater than alpha, I DNR. I do not reject H naught. That's very important. If my p-value is big, that means I'm not a special or significant data set at a 10% level of significance, of course. In fact, pretty much any level of significance you care about. This is also a non-sensitive p-value. And that's why some people like the p-value approach. What type of alpha would this be, smaller than? Alphas that we don't care about, right? Our alphas are 1, 5, and 10%. This number is greater than 1, 5, or 10%, which means you would not reject at all levels. And since we don't reject, I'm not building a confidence interval, right? I didn't destroy the fact that I'm different than 80. I don't think I'm different than 80. I'm probably going to guess we're probably close to 80 again because I did not reject. So let's write our summary. I do not reject H naught. Remember, H naught was pi is still 80%. I don't have evidence to lend support to that. Why? Well, because my test statistic, and when you read journal articles, you should look at that. My test statistic, you'll see that. Your test statistic is populated. It's negative 0.35. That's not in the critical region. Most of the time, if it's not above a 2 or below a negative 2, it's nothing to even be excited about. Most critical regions start around the 2s. And of course, that's why people love the p-value, because the p-value gives them how special their sample is. Your p-value here is big, and that's not good. If your p-value is big, which is greater than alpha, and in this case the alpha 10%, that's not good. Both of these lead to the fact you do not reject. What does this mean? This means I do not have evidence. That's really what it means. I do not have evidence that the proportion is not equal to 80%. That's what I have. I don't have evidence that the proportion of drivers driving with cell phones is any different than the 80% you've given to me. And we can say at a level of significance equal to 10% if you want to add that into your statement. Again, I don't have any evidence at a 10% level of significance that the proportion is any different than the national statistics. What does it mean? Most likely the law has not deterred anybody. All right? The law has not deterred anybody from driving any different, according to my data. What do you do from that? Your choice. Make the law even harsher? You could do that, right? Oh, that didn't have any effect? Let's make the law even harsher, all right, to really curve the number of people driving. You could do that. You can slap on a fine, slap on a driving violation, give points on the license, right? You could do a lot more things to make the law even worse, to really make people pay attention to the effect. All right, guys. Thank you for watching this video. Stay tuned for others.